Good morning all. I've spent the last day or two building this sort of first build of my 8-bit breadboard computer. And here it is with lots of nice flashing lights. That's what we want after all. So this one is a clock. There's a 555 timer there just running in astable mode. These 4 LEDs are a binary count. So there's a 4-bit binary up counter there. So this is counting from 0 through 15. And those are being used to address a RAM. So we're only looking at the first 16 locations in RAM. I did have another chip here to count up to 256, but to be honest, counting up to 16 is a lot easier when you're stepping through RAM locations trying to program them. These are the 8 switches used to program the RAM, and that's the write switch to actually write that byte into the RAM at whatever address is currently on the address lines. These are 2 decoders, LS138s. They're 3-line to 8-line decoders. And here are 3 chips, which are 8-bit, what I like to call peripherals. So these are on the data bus of the computer. And the whole point of this computer is that you can, by programming the program memory with different instructions, you can transfer or copy data from one position in this arithmetic logic unit via the data bus to another. That's how it works. So at the moment, every instruction in the program memory is this. It's 0001, 0001. And what that means is read from peripheral 1, which is this one in the middle here. This is 0, 1, and 2. Read from peripheral 1 and write to peripheral 1. So what we're doing is reading from this latch and then writing back to this latch. Now this latch has been configured, so all its inputs and outputs are skewed by 1 bit, so that every time you write to it and then read back from it, the data is rotated around, is shifted but rotated because it's shifted off the end and then back into the input at the beginning. So I've made a label for the 3 peripherals. This is peripheral 0, peripheral 1, and peripheral 2. That's not an easy word to say, is it? Okay, so peripheral 1, which we are both reading from and writing to, rotates the data in it clockwise. Now these LEDs don't show you what's on the output of any particular latch. They show you what's on the data bus. The way this computer architecture is constructed, the data bus is always showing something. So what we're seeing is a read. We're seeing the read of whichever device is currently selected, and it's device 0001, so it's device 1. So we're simply reading this chip constantly. We're also writing to it, which is what causes this transfer of data in this clockwise direction. Now I don't know whether this is shifting left or right, I can't remember. It doesn't really matter. For the purposes of this setup, this is all kind of visual. So if we read from and write to peripheral 1, we see that there's a clockwise rotation. If we read from and write to peripheral 2, which has been wired with all the lines skewed the other way, there's an anti-clockwise rotation. So what I want to do is find my screwdriver, reprogram the program memory. So instead of 1, 1, it's read from 2, write to 2. So that will read to, write to. Let's fill the memory with that. I'm just holding the right button down while it goes through all locations. Okay, so every memory location now has 0010, 0010. So that's read from 2, write to 2. So we're reading and writing to the anti-clockwise rotating latch. And you can see that the data rotates anti-clockwise. So that's with the computer free running. Now if I slide this little slide switch, I can put it in single step mode, and I can press this switch to single step it through all of the program locations. That's 15 or F. That is 0. So now what I might do is have in the first 8 positions read to, write to, and then let's click through to address 8, and in the next 8 positions I'll do a read 1, write 1. And I've got to program these in, so I want to write into that location. Actually, I can hold this right button down and just step through all of those upper memory addresses, and that should be it. So now, starting from 0, it's read to, write to for 8 memory positions, and then it's read 1, write 1 for the other 8. So what it'll do now is run anti-clockwise for 8 steps and then clockwise for 8 steps. Let's put it back into free run mode, and you can see that half the program memory is filled with one instruction, read to, write to. The other half of the program memory is filled with read 1, write 1, and we can see that we've got half the time it's going clockwise, half the time it's going anti-clockwise. So half the time it's reading and writing to this latch, and the other half of the time it's reading and writing to this latch. Now if I put it back into single step mode, we can have a look at the biphase clock, because we need to read and write on opposite edges of the clock. So if I do this, if I press this switch and we watch the peripherals, when I press it, we do a write so that the data changes state. When I release it, we get a program count increment. So press the button to do the copy between one peripheral and the other. Currently we're copying between peripheral 1 and peripheral 1, writing to there and reading back from there. Release, and we get the next increment of the program counter. So copy, increment, copy, increment, copy, increment. So that's the biphase clock. It's a very simple, just a 2-stage clock. It was the simplest thing I could come up with, which actually enables read on the increment of the program counter and a write on the other phase of the clock. So that's a write, and that's a read, that's a write, and that's a read. So this computer only has one instruction, and it's simply copy from one of these peripherals to another one. And at the moment I'm copying from one peripheral to the same peripheral, but I could copy from, say, peripheral 0 and write it to peripheral 2. Peripheral 0 is set up so that all the inputs are hardwired to either low or high, and in fact 7 of them are hardwired low and only 1 is hardwired high. That's how we get this one dot of light and all the other LEDs are off. So the only instruction you can program into this computer is a copy. You specify the from address and the to address, copy from that address to that address. So it's very, very simple to interpret these LEDs, these instructions, even though they're just binary numbers. It's simply copy from there to there. Right, let's just switch off and on again. This switch is a bit dodgy on the power supply. Okay, that seems to have worked okay. Now I'm going to free run it. And of course the program memory contains just rubbish. So it's reading and writing probably mostly from non-existing peripherals. They don't exist, so of course the data bus goes dead. But every time it reads and writes from a peripheral that does exist, the data bus briefly lights up, but it's a bit random. So let's do the read from 1, write to 1, which is the clockwise rotate. Let's fill the memory with that instruction, and we get the clockwise rotate. The problem is, when I switch this off and back on again, this latch, now we're actually looking at this latch, so these lights are really representing what's coming out of this latch in position 1. 7 of the LEDs appear to be on, and 1 of them appears to be off. So we've got a clockwise rotation, but it's of an off LED. We want it really to be of an on LED, and that's why I built this constant, this literal, this immediate data value, where one of the LEDs is on and all the other 7 are off. I don't really know which one it is, because I haven't actually defined which is D0 and which is D7. They're just arbitrary at the moment. But what I want to do to restore the single on LED is put one instruction in this memory that loads from 0 and copies to 1. That means we load in this literal and put it in this rotate register, and that should change the data from 7 LEDs on, 1 off to the other way around. So let's put that instruction on here, load from peripheral 0, write to peripheral 1, and I'm just going to punch that in at one location in memory. It doesn't really matter which location it is. This is just cycling around all 16 program memory instructions. Bang it in, and now you can see that most of the time it's doing read from 1, write to 1, which does a rotate, but just once in the cycle of 16 program instructions, it's doing a read from 0, write to 1, which pushes this immediate data, this literal data, into that register, and then continues to rotate it clockwise. Now there's probably random data in register 2 as well. We're not going to know that unless I rotate register 2. Let's do that. Let's go to read to, write to, and fill the memory with that. And yes, the other rotator, the anti-clockwise rotator, also has corrupt data in it. The data I don't want. I want a single LED light. So once again, I'm going to do a read 0, and this time write to 2. So read peripheral 0, which contains this immediate data, and write it to the anti-clockwise rotator. Just want to do that once in the cycle. So once again, we can now see that most of the code is read to, write to, but one of the steps it does a read 0, write to, which picks up this literal value from peripheral 0 and writes it into peripheral 2, the anti-clockwise rotator, and for the rest of the program, it just rotates. Now currently my arithmetic logic unit, which is basically these 3 peripherals, only has the ability to load in a constant and rotate it either clockwise or anti-clockwise. So it's more of a logic unit than an arithmetic unit. It doesn't do any arithmetic maths, it doesn't do any adding, but there's nothing to stop me putting an adder in here. It would simply be 2 latches to latch in the data for the 2 inputs of the adder, and then probably 2 buffers to read the data out. Well, one of the buffers would be for reading the result, so you'd have 2 8-bit inputs, an 8-bit result, and the other buffer would be to read the carry, because in an adder you've got an 8-bit result plus 1 bit of carry. You'd have to read that, and that would have to be from the other buffer. So it would require 2 latches and 2 read buffers. They can be on the same address. Yeah, you could load data into an adder and read the result out. So by adding more of these arithmetic logic units and putting them on different addresses, and this can address, well, 8 devices for read and 8 devices for write. That could be expanded actually to 16 devices for read and 16 devices for write, because the read address is 4 bits, the write address is 4 bits. So you could have a very big arithmetic logic unit with adders, exclusive OR gates, AND gates, NAND gates, and all the arithmetic and logic functions that a computer might need. Right, so now that I've got known data in my bit shifters, I want to do a Knight Rider program. So I'm going to stop the clock, set it to address 0, and I want to do 8 clockwise rotations. So that's peripheral 1, so it'll be read 1, write 1. I'll put 8 of those in, so write that into up to address 7. And then on address 8, I want to do read to, write to. That already seems to be in there. Read to, write to. Let's make sure. No, that's not correct. So I need to put in a read to, write to. Put that one in there. It's in that one, it's in that one, and it's in that one. So I've got 8 read 1, write 1s. That's clockwise rotations. And 8 read to, write 2s. That's anti-clockwise rotations. Let's run that. And we should have something a bit like Knight Rider. Now it's not very organized because we're not actually reading the output of a latch. We're actually seeing what's moving across the data bus. So it's a little bit jumpy, but that's essentially it. We've got a clockwise movement and an anti-clockwise movement. The dot moves from one end to the other and back again. Knight Rider. So I want to add a few things to this, of course. I want to add a lot more of the arithmetic and logic processing units, these peripherals as I call them. I also want to add something where this simple loop, which simply goes around all 16 addresses and jumps back to the beginning, it's so simple it's not really practical. I want to add something a bit like Arduino's setup and loop, so you can run setup once and then loop round. So what I want is some sort of mechanism where this thing can be made to, when it gets to the end of memory, jump back not to the beginning but to a point after a piece of setup code, and that address would be programmable with dip switches. Because there's no ability to have a setup in this program, you can put a setup in the loop. In fact, I might do that now actually, because this is not rotating from a sort of known start point. So let's just stop that. Let's go to address 0. Okay, I got lucky. It happens to be on address 0. And rather than read 1, write 1, in that location, I'm going to read 0, write 1, which means that it puts this literal value, which happens to be that LED, into the clockwise rotate register as the first step of the program. So let's run that again. There's the run switch there. So now you can see that we read 1, write 1 and read 2, write 2, but the very first instruction is to pull in the literal, and now it starts from this sort of known start point, kind of. As I say, we're watching the data bus, not a sort of defined latched piece of data. But yeah. But anyway, there it is. Nice simple computer. It's 1, 2, 3, 4, 5, 6, 7, 8 chips at the moment. It's programmable. You can program the program memory with these switches. You can single step through the memory when you put it into single step mode. And you can copy data from the 3 peripherals currently that are in the arithmetic and logic unit so that it can compute. It is a computer. Cheerio.